Welcome to mini project 4, where we're going to look at convolutional neural networks and another Kaggle challenge, although we won't be actually doing it as a Kaggle challenge, a humpback whale identification challenge. I suggest you look over this challenge. In fact, for the write-up at the end, you're going to have to write a quick summary of this, so you might want to just do that when you start. So humpback whales are a common whale that is sighted, and as they swim, they often dive down, and you can see their tails showing. And there's lots of pictures of tails, and people have learned that you can often identify whales by their tails. This was one of the first Kaggle challenges that I led a group of students working on this challenge a couple of years ago. It's also about the same time last summer we were visiting my daughter out in Seattle. She recently moved to Seattle, and we got to go on a whale tour, and we actually got to see a humpback whale and a whale tail, so that was exciting. They were able to identify the whale this way on the tour. Well, actually after the tour, because they took pictures of it here. And I think it's a good example of convolutional neural networks applied to image recognition that shows how they can have an impact on things. It's not tied to simple, identifying if this is a cat or a dog or else some business problem. It's a little more general problem. So I like this problem. So similar process here in this notebook. We have to import our libraries here. And now we're going to read this data from GitHub. I've got this out in GitHub rather than from Kaggle, and the reason why is that the original database has 41,000 images of over 600 whales, and it's nearly 7 gigabytes of storage, which is too much to bring into a collab. The amount of time to load it in, even just load it in, is too much, and I don't even know if they have enough space in these collabs for that many images. And then the training time often takes more than 12 hours, especially with this many images and stuff. And to get good results, we are often running this for 24 to 48 hours of training. So in Colab, shut down the limit on run times are 12 hours. So, and again, I don't expect you to be running this for long. So we've simplified the data. We are looking at only the 200 most common whales, and we only have about 10 images per whale. So that brings our data down a lot. So what this does is actually copy this folder up, and these are actual image files. If you look here, there should be here a folder called CIS 6115 whales. You may have to hit refresh to see this after this is loaded up. And then if you look in this, there's a training folder for the top 200 whales. So there are 200 folders here. Each whale has an identification ID here, so it's the W is for whale, and then that's the ID number. So I can actually look at that whale. I can actually open these up, and you can see these images of whales here, whale tails. And then you can go into different whales and look at different whales and the different whale tails. These are big color images, and the idea is if you see this whale and you later see another image of the same whale here, can you identify that this whale, let's get the same, see this fin here and like that mark and this mark, and now you see it here, is that the same whale or not? This is a very hard challenge, and so you're certainly not going to get 90% recognition, maybe 50% recognition on these. Also, these are big. There's lots of different images here that you can look through, but those are all over here. Okay, so we read those in. We'll actually run this script that displays some of the sample whales. So these are just 2 sample whales. I just picked 2 whales in particular. Their folders are here, and I'm just displaying their images here. So again, you can kind of see this one with all these little spots on it, and here and here and here. And so I think we could see a couple of these and maybe learn to identify these as the same whale. Here, this looks like that same whale, and then again this whale with these white spots. So this and this, they look like the same whale. And again, does this look like the same whale as this and this and this? And so that's what our network is going to try to do, is identify that. Okay, we do a number of setup things here, but what I'm going to do is set up a basic network for you to use, and then I'll let you adjust it here. Because again, we're just getting into these neural networks, and so I don't expect you to be able to do all these. So I've set up some learning rate and early stopping checkpoints here, but so those are available if you want. But again, you don't have to change any of this code. You can just leave this code be here. So I'm going to just run this code, and then we're going to set up our folders. And so again, our folders are over here, are in this CIS 615 whales folder, so we have that, and inside that we're going to bring in our training data, and there's also a set of validation data that were a bunch of images that we're not going to train on. So we're going to set up both of those folders for us. This is set up because you can actually download all this to a local computer and run it there, but we're running it all in Colab, so we'll just leave this as is here. Now, something's a little new here. When we're training on actual images in folders, we're going to use this data generator here. We're actually going to use two data generators, one for when we're testing and one for when we're training. And we can do a number of things here. One of the things we're going to do, if you remember, with images, they're often values, each pixel is a value between 0 and 255, and we want a value between 0 and 1. So we're going to rescale all the pixels. We're going to take each value and divide it by 255. And we're going to do the same thing when we test and when we train. But we can also do other things. We can do things like flip. If we want to do some image augmentation, we could randomly flip some images. So we could set this to true to randomly flip some images. If we wanted, that would double the number of images we have, because again, here, and again, you can ask us, does it make sense to vertically flip though? And probably not in this case. But we can also do some automatic random rotations and zooms and other features here. But that's, again, you can actually just leave this all alone and you don't need to modify this. Right now. If you want to come back later, you can. We're also going to read these images from these folders. So these folders are already set up, and so we're going to read these in. We can't have all these images into memory at the same time. They're just too many images, too much memory. Here again, the original thing was 7 gig of images alone, and so it's just too much to bring into memory with the network sizes and stuff just for the data. So we're going to use this. There's a special method. Once we have this image generator set up, we can flow from the directory, and that'll automatically bring the images, load the images in, and optimize some things as it reads the images in from the different folders. Here. In order for this to work, we need a folder for each category, and so there are 200 folders, one for each whale, and so we have to make sure we've broken up the images. So all the images for one whale are in this. These are all images, pictures of this one whale, and that's how it has to be set up for this flow from directory to work. So we set that up. We also going to resize the images. Some of these images are very large color images, and so we're going to resize them to 256 to 256, and sometimes you may have to change this for some of our other models. Okay, so and that again, you don't necessarily have to change anything there for now. And now we're going to set up a deep learning network, and you have a couple options here. The first thing is you can define your own neural network structure here. So here's what we've seen before, where we're defining our own network structure. We're setting what the input size is, the number of outputs. There's 200 different whales, and here's our sequential network, and we're doing it. In fact, this network is the same as in your book. So if you look in your book when we start talking about CNN architectures here, they go over a sample. They talk about this layer, and then they go over this sample where they use a convolutional neural network here. This initial layer, actually, rather than a 3x3 filters, has 7x7 filters and 64 of them. They're using this on the Mint's data set, so their image size is smaller than ours, but we're changing that. And then they do max pooling, and then they do 128 layers that are 3 by 328. So again, they have this architecture. They describe this here, so you can look at that. And so that architecture is what that. I mean, I just copied that code in here. So this is that code, setting up this architecture. We print out a summary, and then we compile that. Network. So here's the view of that network. We start with 256 by 256 images. We have 64 filters applied to that. Then we pool it down to 128 by 128 images, and we add more filters here. We pool that down to 64 pixel by 64 pixel images, and we add more filters. We pool that down to 32 by 32 image with 256 filters or layers on that, and then we flatten out that image, and we end up with a lot of parameters, and then we have a couple dense layers. It uses these dropout layers. We haven't talked much about those, but these dropout layers help randomly drop out certain weights, and they kind of help for overfitting, and so those are commonly used. I guess we'll talk about those in a couple in an upcoming unit, but those I left those in because they were in the thing. You could actually comment them out if you want. One thing to pay attention then, and we finally end up with a dense layer with 200 different whale or units, one for each whale we're going to identify. One thing to watch here is the total number of parameters. Is the total number of weights that can be adjusted. There are over 34 million weights in this model, so this is a very large model. It's going to take up a lot of memory for it to work. So that's one option, to define your own network structure here. Another one is to load in some architectures. In your book, it talks about some well-known architectures, the LeNet, which was one of the first ones that worked with this kind of, they defined what a convolutional neural network was back in 1988 by Lee Chung, and that and later on there was the AlexNet, which again was around 2012, and it won a challenge there by how it was set up here. One thing with these things is that the way they lay out here are kind of opposite the way we have to lay them out. When we show these, we start with the input at the top and the output at the bottom. Your book for some reason shows the input at the bottom and the output at the top. So just so you know, when you read these, it's kind of upside down. So here's the input, and then work up, and this is the output up here for that. So they talk a little bit about data augmentation, how you can take one image and like rotate it or change the contrast or crop it or different things here. And again, that's one of the options you have. You don't have to do it, but again, up here I've actually commented out, but we have a link up here talking about some of the what you can do with image generation. But you can do some automatic rotate. You can automatically rotate images by up to like 5 degrees here, or you could flip them or shift them over left or right or something like that. So when you have very few images, this is a nice way to randomly add to those images here. Okay. So that's here. But here, okay, now we're getting into Google, the GoogleNet, LeNet here from 2015, which is a really interesting, more complex structure. So far we've been looking at a sequential structure where we've had one layer feed to another layer. So let me go back up here. So we had sequential, one layer leading to another, but Google developed this really complex situation where rather than having one layer lead to another, they'd have a layer here, and it would feed into 4 different convolutional layers, a 1-by-1 convolutional layer, another 1-by-1, all these 1-by-1s. And again, the logic behind these is rather interesting. They do amazing little tweaks to the data. Here you wouldn't think so, but they do. And this feeds to a 3-by-3 filter, this feeds to a 5-by-5 filter, and this feeds by a 1-by-1 filter after it does some max pooling here. Again, the logic behind this, and then we combine all these different filters into one category, which is about the same size as the original image that was fed in down here. We concatenate them all together and we feed. So this is what's called an Inception model, or an Inception layer. It has all these sub layers or sub filters in it, this Inception model. And then Google built a model from that. Let's see where, I think that's described here. It is where the input comes in. Again, they do a 7x7 convolution, max pooling, some a 1x1 and 3x3 combination, some max pooling, and then each one of these is one of these inception layers here. And one of the questions is how many filters in each of these there are, and they're actually showing them. This shows how many filters of each of those sub parts there are in this. And so there are a whole bunch of filters, 6 filters applied in this module goes to another one of these inception models. They do a max pooling to shift the image down to a smaller size on a bunch of these inception models, another max pooling and stuff like that. And finally, a fully connected 1000 unit layer here, and then their softmax layer. So this was this Google net architecture, which was the largest network at the time. We'll actually provide, I'll see if I have a version of this we can just load in. I'll see if I can load in a version of this with the whale challenge to show you, because we don't have a pre-built version of this here. Okay, VGG net. There are 2 different versions of this, the 16 and the 19 one, depending on how many filters was. But again, this is around 2014 when it was developed and used, and it's a standard architecture here. Now, what we can do is we can bring in these architectures. So some of these you can actually define here, but again, they get quite large and you have lots of layers. There'll be multiple pages of network definition. So instead, option 2 here is to load in a pre-built, oops, I didn't mean to double click on that, a pre-built CNN architecture here. And for example, VGG16 is one here. So if we want to load that in, we just simply define the input and output size, and then we say here, to use as a pre-trained model, load in the VGG16 model here. And you can actually say, I want pre-trained weights with the ImageNet data set out there. The ImageNet data set is a huge data set out there of a whole bunch of images that is kind of a stat. So there's 14 million images out there in this data set. So it's a good way to kind of initialize the weights on a lot of things. Now we can ask a little bit about issues with how you pre-train weights and if you introduce some bias based on that. So that is an issue sometimes when using pre-trained weights. But again, we can bring in that VGG weights, and in fact there are a number of different models that are available out there. Here's a list of Keras applications or pre-built models that are available out there. So like VGG16, it takes it's a model that takes 500 megabytes of memory. It shows some of its responses. It has over 130 million weights or parameters in it, and it has over 23 different layers to it. And again, there are some other modules we'll look at here that you can read in. So these are pre-built ones. So when the book talks about this VG net, we can just bring that in, we can just load that in here. Now the book really doesn't talk too much about that structure, so I've tried to link in some things with that. So the first thing is the paper that defined this and showed its winning score on here. So this is just a link to that actual tech paper that you can view from Cornell of the people doing that. It's a little hard to read, but it's kind of interesting to see the original paper from 2014. And here's the general structure. We have an image. They expect images to be 224 by 224 by 3, so 3 colors, color images here. And then they have these layers, max pooling, a couple more layers, max pooling, a couple more layers, max pooling, and they pool down to a 14 by 14 with 512 12 different filters or layers at each one of these images, and then they finally drop down to a 7 by 7 by 512 layer, and then they feed that in, and their dense layers are 4,000 nodes large that they feed in. They have a couple of those, and again they're feeding into a 1,000 node image here. Again, this is another view of that structure. So I just wanted to show you I like this graphic, and so I included that in here also. Okay, so that's one. They also talk about ResNet. This is another structure where they're trying to do deep learning. So rather than doing this layered sequential approach, we have input going to a layer 1, going to a second layer. What they're doing is that they're sending the input to layer 1 to layer 2, and then they're going on to layer 3, but they're also letting layer 3 look back at the original input, or look back 2 layers at whatever the value was before this. So this layer up here has 2 different inputs or connections. It has connections to layer 2 and then connections back to layer 0, or the layer that's before this, and these are stacked on top of these others. And the idea is that sometimes it's useful not just to look at these high layer features here, but also to look back at the lower level features at the same time for this. And there was a lot written. This is from 2015, but this is called residue networks or ResNet structures, and there's a little more description of here and how these are set up. But again, these are available. Here's another link, description to the actual paper, and a link to the descriptions here. Here's again another guide to Inception layers and a combination of Google Inception Nets with ResNets out there, if you want to read. We can load in these networks, but there are also a couple other networks that are out there. There's a DenseNet 200 and an exception layer here that are also available. Like I say, if you look in here, this will show the ResNets you can load in. Different than there's been a number of versions of ResNets. You can load in the Inception network here, Google's Inception Networks here, the DenseNet values here. Some of these are nice and small, only 800 megabytes, only 20 million, small relatively here. And if you click on any of these, you can see some of their values. Okay, so in our code here, I just show how to load in a couple different models here. But again, you're welcome to use any of the models that are available out there for this. A couple things to watch. When you do these models, you can either say initialize the weights to ImageNet, and I recommend you initially start with that. It'll speed up training quite a bit. You can also try weights equal none, where you'll just get random weights to start with for this. Okay, sorry, I cleared that out. Okay, so you can either use random initial weights like we've always had, or else use these pre-trained weights. We do generally probably want to say the pre-trained model is trainable. Because we're doing something very specific on whales identification, we want all the filters, all the weights throughout through the pre-trained model to be modified. They will initialize to this, but we can the learning will go through that. There's sometimes where you're going to pre-train on something and you don't want to adjust those the pre-trained model weights at all, but in this case we want to do that. So here's where we're building our sequential model, and again, if you remember before, we built a sequential model and we listed out all the layers here. Now our first layer is just the pre-trained model, so we define a variable up here called pre-trained model, and we load in our pre-trained network, and then we're going to do some pooling from that network, and then add our output from that network. Now we could add a couple of dense layers here if we want. Now one thing is that when we load in these models, we're going to say include top equals false, and that will chop off the top dense layers and the top output layer, because again our output's we only have 200 whales that we want to identify, so we're going to not include the top couple layers of these networks. And so that's why we've had to add this pooling layer here, and then this dense layer for softmax. And again, if you wanted to add a lot of these networks add a couple of these fully dense layers here, you can certainly do that. Okay. Now we're going to compile these. Here we're going to use an optimizer, and again later on in units we're going to look at what different optimizers are. For now you can just leave this the way it is. You don't have to change this. So you can just change the models, you can leave that the same. We're going to print off two summaries. One is the pre-trained model and one is the final model. So let's go down here. If I look, let me scroll down, this is a huge model. Okay, here's the final model, and it just shows we're bringing the exception model here with 20 million parameters, and we added max pooling and then a dense layer for that, and here's the total number of parameters. When you report on things, you should report this total number of parameters or weights in your model that you have. But it's nice to sometimes see this the model, the pre-trained model you loaded in. So this is the pre-trained model here. So this is the actual, we have this variable, we define pre-trained model up here. Oops. Yep, pre-trained model up here, and we use that in our network. So we can just say, give us a summary of that pre-trained model, and that's what this is. It's called, the model is named, is called exception, and here are all the different layers. We started by 256 by 256 images. We immediately cut those down, pooled them down to a 127 by 127, and then all this sort of stuff. We have all this. We bring them down to 63 by 63 images, 32 by 32. We eventually end up with 16 by 16 images with 728 layers or filters applied to those. And we have a whole bunch of them, and again some of these are connected in different ways here, so there are some interesting connections being made, and again a whole bunch of that stuff goes on at this layer, a bunch more of that stuff, so lots of trying to find interesting features of this. And again, these are actually different Inception models that are combined together and then added here. So this is similar to if you remember the exception model. Well, the Inception model from Google had, instead of just one convolution layer, they had 1, 2, 3, 4. They had 7 different convolution filters applied and then concatenated together. And this is doing similar stuff. So this should be the different convolution or filters being applied in different ways, and then all concatenated together before being pooled together. So you'll see this structure again and again, where you have a whole bunch of these filters built together and then added together before being pooled. So that's why this looks, each layer is actually 7 or more filters long, and you'll see this structure repeated again and again throughout this. Okay, but again, you don't need to necessarily understand that, so you can just load in the model, see how many parameters, and try it. Now we're going to train this network here. The main thing you want to watch is how many epochs you're going to train it for. I'm going to show you the results first and then show you how long this runs. It takes a little bit of time. This data is actually should train in not too long, about 10 to 20 minutes. So for this, so again, we're running these trainings. We start, our initial accuracy was only 2%. Again, there's you have a 1 out of 200 chance of choosing this, so we did learn something. But and then it improves to 10%, and again we improve this. This gets up to almost 90% accuracy with this, with the training images. But for the validation images it hasn't seen before, we get up to 64% accurate, and that's really good with this pre-trained model here. And then we can plot the loss and the accuracy, and again we're kind of almost overfitting. Our training percent is getting way up here to 90, where our validation accuracy is a little lower, down in the 60s here. And again, when you run this, it will take a while to run. But again, I've tried to scale the data down to a manageable size so you can just run it. So you can just click on this and let it run. Here it's going to run through 150 images, train on 150 images, and then move to another set of 150 images for this. And we'll see the accuracy. Actually, since I didn't redefine my network, it's actually it's building on the previous accuracy, so it was already up to 90% accuracy. So it's trying to increase that. It'll run through that. It'll run through training on 150 images for one epoch, and then it'll do validation, and it'll look at 20 random of the testing images that it hasn't seen before and see how accurate it does on those 20 remaining images. So that's this validation accuracy is only 66% on those random 20 images it looked at. Here, and then again we're going to train this again, and each of this it's taking about a minute to go through and train on 150 images, and right now we're only doing that for 20 epochs. You might want to change this. It's not uncommon to train to train this on 100 epochs for this sort of stuff to get the top results. But again, that's going to take over an hour to train, so you have to balance that out. But again, we can just let this run for a while. I'm here. Okay, so what do you want to do for your write-up? Sorry this is taking so long. So three things when you write up. First, just write a quick summary, a paragraph, read about the whale challenge again from the Kaggle thing, and write in your own words, just a paragraph kind of summarizing what you've learned about that. Then you want to try out 3 different configurations, train 3 different models, and each training again will take 20 minutes or more to an hour of training time, so give yourself enough time. So some things you can do: certainly you can try out different neural network architectures. You can create your own architecture. You can try out any of the pre-trained models here for that. Also, you can decide if you want to use pre-trained weights or not for that. With the pre-trained models, you can add additional dense layers. So again, when we go up here and we define our models, skip over all this. Okay. When we define our models, we can say whether or not we want weights equal none or weights equals pre-trained on this ImageNet data set. And again, we can, when we layer we bring in our pre-trained model, we have to do this global average pooling, we have to do our output layer, but we can add these dense layers in the middle here if we want. Or you can do other layers if you want, whatever you want there. But that's the most common choice. So those are some options. You can try to change the image size. Sometimes you may have to do this for some of the pre-built models, may require images to be a certain size, and that's from directory. I have to not double click. Okay. All right. And then you can also add some image augmentation from the image generator. So let's scroll up and remind ourselves where those were. So up here, where flow from directory is, here's where we specify what size we're resizing these images are. The top actual winners in this competition on Kaggle resized images to 512 by 512, but again, that increases your training time, and you have to generally add more layers to your network and stuff like that. But again, and some of the networks may expect different size images here. And the other thing is you could add some different scaling and stuff. Now you generally do not want to do any fancy image augmentation to your test data. You want to make that as easy to test as possible, but while you're training you can add some horizontal flips or random horizontal flips or random changing of the lighting or shifting or something like that. Try that. Be careful, don't do a whole lot. It might seem like a good idea, don't do a bunch of this, but again, in reality, often doing this will quickly degrade performance. So try to keep, I would suggest, try to keep this to a minimum if you try to do some of this stuff. Okay, so you've got to train 3 different networks. How's our training coming? Well, we're already to 7 epochs here. Okay, your try 3 different network configurations and report back. How many parameters were in the model? How long did you train the model? Number of epochs? How was your accuracy? You know, what was your what did you choose? What model? What your architecture was? So just describe 3 different models. This is a good thing to post to your discussion area. So feel free to take this when you get a result and post it to the discussion area so people can see each other's results if you want. And then finally, just to do a summary of what your results are. You did 3 different models. Do a quick analysis. Why do you think the results turned out the way they did? So just a short paragraph of that. Okay, hope you enjoy this.